Good evening. It is 7 p.m., but nobody has joined yet. So we'll wait for a couple of more minutes before we start. Good evening, Indranil. We are waiting for more people to join, so we'll start in some time.
Okay, sir.
Good evening, everyone. Let's get started. I welcome you all to week 8 of live sessions for the fundamentals of additive manufacturing technologies. I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. I work broadly in the area of additive manufacturing. As usual, our agenda would include a recapitulation of the concepts that were covered this week, then certain conceptual or numerical questions which will help you to better answer the assignments that are due. And I looked at this week's assignment. So in terms of numericals, they were all direct formula application based questions, and even the conceptual questions were directly from the slides. So you should not have much trouble this week. So the first lecture this week covered MIG-WARM process, and it is basically borrowed from MIG welding. So the process is pretty much similar, except in this case we use the material deposition to achieve a free-form shape or a final built part. This is a typical MIG-based warm deposition setup. So I guess most of us would be familiar with this. And for MIG, we know that the electrode is consumable. And here the consumable electrode would be in the form of a wire reel. Also, the feeding rate or the velocity with which this wire is fed is also intricately linked to the current. So they cannot be controlled independently. So the current flowing through the wire is linked to the feeding rate. The welding torch is connected to gas supply cylinder, which provides the necessary inert gas. And what type of power supply is used, we'll check in the next slides. And as mentioned, the current from the welding machine is affected or changed by the rate of feeding of the electrode wire. So we can have three setups. The workpiece can be positive or negative, or in case of a DC source, or if we are using an AC source, then that is the third type. And each of these have some unique characteristics and situations where they might be useful. So for DC based machines, DC arc welding is generally preferred because it offers a good heat input which can be controlled. And 70% of the heat from a DC heat source is liberated near the anode. Thus, it would be helpful to actually uh, have the workpiece as an anode and the electrode as cathode. And if more heat is required at the workpiece side, logically the workpiece can be made as anode, which liberates a large amount of heat near it. This is known as straight polarity or technically the direct current electron negative. Again, it would give to a good extent of penetration. So we are well aware that uh, this would be the penetration depth, say if I denote it by dp, and this would be the height of the melt pool or the height of the deposited bead. And depending on the ratio of h and dp, I can calculate my dilution. Mm. A good amount of dilution is necessary to prevent delamination as well as good metallurgical bonding between deposited layers or between a layer and a substrate. Anywhere between 10 to 40 or 50% dilution is recommended. Again, if you are still using a DC source and our polarity is reversed, or in case we desire less penetration, we can use a direct current electrode positive case, where actually the workpiece is said to be the cathode. And here we see that the amount of penetration is pretty less. Again, in certain cases, the AC welding or AC power source may be useful, especially where we are dealing with materials which get oxidized easily. And what would happen is because of the continuous reversal of the polarity of the electrode and the workpiece, the surface oxides can get broken up. And in the next cycles, when the polarity is reversed again, they can be deposited. So depending on our usage, depending on the end requirement, we may choose the power source as well as the polarity of the substrate and the electrode. Again, different types or different mechanism of metal transfer may be used, and each would have a different deposition rate. Here we see that in order of increasing deposition rate, except this is an aberrant entry. We have the methods such as short circuit transfer, globular transfer, spray transfer, pulse spray, and rotating spray transfer. Also, the current increases as we go down. So in this slide, all the different methods were explained, and usually the most suitable, which is used for warm, is actually the pulse metal transfer. So in pulse metal transfer, you have two currents operating, or basically you have current in pulses. So if this is the time, this is the current. So you will not have a monotonous or a constant current. You would have them in pulses, such as here I have a square pulse. So here the minimum current of this pulse would actually correspond to what is called background current, and the peak current. Each of these serve different purposes. So the background current is actually used for generating and maintaining the arc, whereas the peak current is what actually leads to melting of the wire and metal transfer. And in the case of this pulse metal transfer, we'll see continuous pulses of light. So it'll grow brighter and then dim down again, which is when the metal droplet is formed and subsequently transferred. Also, we have the rotating spray metal transfer types, where the metal does not really fall vertically down, but actually forms like undergoes some sort of a rotary motion, and thus can be deposited across a larger area. In short circuit metal transfer, the amount of current is the least, as well as the amount of the metal transfer is also the least. And why is it called short circuit metal transfer? Is because so often the characteristics of such sources would be something like this. So, so this is the voltage and this is the current. So almost flat type of characteristics. What this accomplishes is so to achieve even a small change in the voltage, the change in current is pretty large. Thus, in case of short circuit, when the amount of voltage drops to zero, the change in current is immense. This immense change in current, because of Joule heating, leads to melting of the wire and breaking of the short circuit, which allows the arc to not be extinguished. Another very useful technology, which is especially suitable for aluminum, is called cold metal transfer. And previously, we saw that once the short circuit happens or once the wire comes in contact with the substrate, it is separated again by increasing the amount of current that is being passed through it, which raises the temperature, melts the wire material, and leads to deposition. However, the difference between cold metal transfer and such short circuit based metal transfer is that here the separation takes place not because of the increase in current or the increase in temperatures, but by mechanical separation itself. So initially, the arc would be initiated and the filler metal moves towards the well pool. However, the current is not as high, and rather than melting, the filler wire actually dips into the molten pool and extinguishes the arc. Again, this leads to a short circuit type of situation, and a retraction motion of the wire assists in droplet detachment. And once the desired gap is obtained again, the process continues, and in the next cycle again, the wire continues to descend into the molten pool. Thus, the temperatures achieved here are also lower than in, say, short circuit based metal transfer. Here we saw a video of how that this wire will travel downwards, and the molten metal will not really detach from the wire until it is in contact with the molten pool. Once it is in contact, the voltage drops to nearly zero, and the amount of current begins to increase. However, it is still not sufficient to melt and detach. Then, once it is in contact, because of a mechanical retraction motion of the wire, The molten metal is deposited into the bead and the cycle continues. So just like any other additive process, even metal inert gas based bomb has a process cycle. Again, we always start with a CAD model. It is a part of the definition of additive manufacturing process that we start with a computer generated CAD model and do the orientation, support generation, slicing, and toolpath generation, all the regular stuff. These processes are maybe called to be part of the pre-processing stage. The next would be certain in situ processes, should we choose to use them. So apart from deposition, we can have some form of in situ rolling after deposition of each layer. We can have some short peening or even laser short peening to relieve the residual stresses from the surface. We can have a hammering sort of operation, which again may maintain Z accuracy or may relieve some of the tensile stresses. And there can be some cooling operation also. And of course, to maintain the Z accuracy or to maintain the geometric accuracy, we can have a face milling sort of operation. Since these operations take place with building or in between the building cycles, they are called in situ processes. And once the process finishes and the part is taken out, or if some post processing or some subtractive operation takes place in the same setup, those processes may be part of the post processing schedule and can include a finishing milling cycle using a face mill or an end mill cutter. We may also subject the built part to some heat treatment to homogenize its microstructure, for instance. And we may also save the NC file, which is the, say, the machining operation toolpath, and then we obtain the final component. Whenever we are starting with, say, a new material or a new process, we would of course want to know what are the optimal deposition parameters, and these parameters may not be always available. Especially, we are aware that a major thrust area in AM research is actually the development of new AM alloys, or alloys which are suitable for additive manufacturing. Also, often we might want to experiment with the suitability of previously unused metals and alloys for additive manufacturing. And a usual cycle to actually test the suitability would be to start with a single bit deposition or a single track deposition. Say evaluate the height of the melt pool or the bead, the depth of penetration, the bead width, and other things. Once we can optimize or we have a grip on the single bead, we can move to a multi-bead deposition experiment. Again, a multi-bead deposition experiment would include laying adjacent beads in the same XY plane. And here we would have to calculate the optimal step over and see what are the types of say metallurgical bonding which is occurring between adjacent beads. Once this is optimized, we can move to a multi-layer deposition where we have these multi-beads in each of the planes and we have multi-layers. And once all three are optimized, of course, we end up with the component itself. Some of the critical process parameters which actually govern all of these experiments or all of these phenomena would be the power governed by the arc voltage and the starting main reduced and final currents. Of course, the wire type, its composition, whether it is coated, the diameter and the feed rate are important. The gas, which can be used as a, say, inert gas to protect the melt pool from oxidation. Also, the gas may be used for generation of plasma, as we will see in the TIG or plasma-based bomb. So the gas flow rate again plays an important role. How long it is flowing, how long after the build does it continue to flow? The layer thickness, bead width, bead height or the reinforcement height are critical deposition parameters. The distance between nozzle and the base plate, also called the standoff distance, or the torch speed, as well as the toolpath planning that we have, or the type of area filling, the step over increment. All of these will actually dictate how the final part ends up. Here we have a very simplified model of the cross section of a single bead deposition. We see that so this part is actually our substrate or the build plate, and we see that the bead has actually penetrated into a substrate up to a certain depth. Say if I just call it by dp, and the bead above the substrate would have a height h and a width w. So for modeling purposes, this profile is actually simplified into a parabolic profile. So it is divided into two. Say above the substrate, this may be thought of to be a parabola, and below the substrate also a separate parabola with a different equation. But yeah, both profiles are considered to be parabolic for the process of this modeling. And in terms of the bead height and bead width, the mathematical equation can be easily obtained. In some basic mathematics, we know that area of a parabolic curve is given by 2/3 h into w. The bead formation is often the interplay of several physical phenomena such as gravity, electromagnetic forces. So as we saw in the case of globular metal transfer, the metal globule will not really fall, say, directly below where it is getting melted. It will not fall, form a very vertical path. Rather, it would have a suitable trajectory which will be governed by the interaction of the Lorentz forces, which include the electric and magnetic interactions, as well as the forces due to gravity, the effect of surface tension, or any vapor pressure or vapor recoil which may be coming out of the surface, as well as it will interact with convective effects of the gas flow itself. The modeling that we have here is actually just a simplified and hybrid form of parabola that includes some of the more easily measurable geometric quantities, such as the height, which can say easily be measured by a vernier caliper. Again, as we were saying that the wire speed is directly proportional to the current, and they are not really independent properties. And thus, when we have a new material or when we have purchased a new machine, a starting exercise would actually be to calibrate the wire speed with the current. Such a characteristic curve is given here on the right. So here, for a given speed, if either of the parameters is known, we can know the other. Say, I'm able to measure that the current that is flowing across is say some 90 amps. Then I know that the wire feed rate is somewhere between say around 7.5 meter per minute. So this can actually help us calculate the deposition rates. So in MIG welding process, the wire feed is in synergy with the welding current, and mostly this curve would be linear, but that is not generally true. It can have a different sort of characteristic also, and needs careful calibration. Now, when we are doing multi-track deposition in the same XY plane, often it will be our say it's a desirable feature to have a flat surface, and the flatness of the surface can only be obtained. So here we have three illustrative cases of how these say multi-track depositions can go. And given an optimum step over distance, three scenarios may show up. So in the first scenario, we have that the surface between the two beads is almost say horizontal, and this can be ascertained if the overlapping volume is equal to the volume of the valley. Say here, this is the volume of the valley, and this is the overlapping volume. Of course, the other cases are say inequalities. So in if the overlapping volume is less, then the volume of the valley will have a dip of the surface. So the surface would be say concave upwards, or the if the overlapping volume is more than the volume of the valley, the surface would be convex upwards. Both of these are undesirable. And based on some simple modeling from this paper, it has been found that the optimal step over distance is, I mean, for a very simplified model, of course, we had as this P, which is actually the pitch of the step over distance, equals 2/3 the bead width. Again, this is a very simplified model and need not represent real life characteristics, but it is accurate enough. Here we have a simple numerical. I think there is a similar numerical in the quiz as well. So just by changing the numerical inputs, we can obtain the solutions. And for given torch speed, bead height, penetration depth, wire diameter, and other factors, welding current also. And from the characteristics, we can find the wire speed. We are asked to find a certain deposition parameters such as the deposition rate or the bead width, the optimal value of step over, and the approximate value of the minimum power required. So formula for all of these have already been derived in the slides, and it's really easy to calculate. Yeah. Now the complexity is introduced in the case where we have, say, multi-layer deposition, or where we are depositing single tracks on top of each other, or even we have adjacent tracks in each layer and we are depositing multiple layers on top of each other. And the source of this complexity is because while the first track that is being deposited is in contact with a mostly flat interface, of course there might be cases where we are, say, you want to deposit something like hollow hemisphere. In that case, there are papers which actually use, say, a hollow hemispherical substrate, and which really allows very easy deposition. But mostly, usually, you would have what is called like a flat substrate, and thus the first bead would have a flat interface to interact with, and the deposition can be modeled easily and observed better. However, once subsequent layers are deposited on top of this existing or pre-deposited layer, they will not really have or not really be in contact with any flat interfaces. Rather, for subsequent beads, the substrate is curved. Thus, the modeling is not the same, or the height of deposition is not the same for the very first bead and the subsequent beads. Thus, the height and width of the bead deposited on a curved base have to be calculated so that the arc gap can be maintained adequately. We know that by changing the standoff distance or by changing the working distance, it will alter the focus or the focal length, and it will alter the deposition characteristics as well. Thus, the quality of the part across the layers will not be consistent. And we might have optimized our parameters for a fixed working distance, but here the distance is changing dynamically. So we might need to account for that change. Again, I'm not going into the details of this derivation, but here we'll have a non-linear equation. So in terms of the sines and the angles, yeah, this one. It can be solved numerically or graphically as shown in the example by Professor Kapil. Also, I think the question based in this week's assignment uses similar data, so that does not even really involve any additional solution step as well. Just by changing the values or the number of layers, we can have the necessary answer. Now, here we have a multi-layer deposition. So the y-axis is actually showing the layer number, and they have measured the micro hardness values by indentation method across these layers. And it is found that, say, till layer number 12, which is here, the hardness value is rather consistent. So here in this case, the x-axis shows the hardness values, Grinnell hardness in this case. But after a 12th layer, suddenly the hardness value increases and increases drastically. And what can be the cause for this change? So it is actually the thermal cycling. And the slide says that hardness variation exists only in the final few layers and falls rapidly within the thickness of a few layers. And that is because of thermal cycling. So I have some additional content to show what thermal cycling really is. Yes. So consider this is a simple simulation I ran in ANSYS Additive for the purpose of this class. So say I'm depositing a very simple geometry here, and it consists of, say, some 12 layers, and I'm measuring the temperature at a certain junction in this geometry, and I'm simply plotting the nodal temperature. So I selected these nodes, and I simply plotted the temperature versus time characteristics as each subsequent layer is getting deposited. So on the left here, you have the plots for subsequent layers, starting with layer 0, 1, 2, 3, and 4. On the right, I have just plotted them a few layers apart. So starting with layer 0, then 3, 6, 9, and 12. So let's try to understand what is happening here. So on the right, you see that the red or the layer in red is a currently deposited layer, and the ones in blue are previously deposited. Of course, we see that the previously deposited layers are almost at the temperature of the substrate itself because of the very fast heat transfer, and the topmost deposited layer is at nearly the melting point. If we come from the top down, we see that for the layer number 12, there is this single spike in temperature, and which is say reaching the nearly the melting point temperature. When we come a few layers down to layer 9, we see that there are these few peaks, small peaks, and then these two high sharp peaks. So what are they exactly? And if I were to just project this one downward, I will see that this small peak corresponds to the deposition of the 12th layer. So what happens is, because of the deposition of the subsequent layers and heat extraction from the substrate, even the previously deposited layers will actually undergo a rise in temperature or will experience a rise in temperature. This is what is called thermal cycling. Say for layer number 9, this small peak corresponds to deposition of layer 12. This one corresponds to deposition of layer 11. We see that they are not really, say, much high, or they would be only around some 20% of the melting point. But even those temperatures are sufficient to perform some sort of, say, in situ heat treatment of the substance. This one is corresponding to the deposition of the immediate next layer or layer 10. And we see that here the temperature experienced by the previous layer is almost equal to the melting point temperature. And this is expected because unless this is achieved, there won't be any adequate bonding between the layers. And without melting, there can't be any penetration, and there will be delamination. And of course, this one is corresponding to the deposition of layer 9 itself. And similarly, for layer 6, we observe these multiple peaks. So each of these small peaks actually corresponds to the deposition of the subsequent layers. And slowly we see that for layer 0, it has some 13 peaks, which are corresponding for the deposition of layer 0 to layer 1. And of course, layer 0 would mean the substrate itself. Similar for the other cases. And we see that these peaks do not really die out. So for the first layer, it would have these 12 peaks corresponding to the deposition of each of the layers. And this is what is called thermal cycling. Now, because of this in situ heat treatment sort of effect, the microstructure of the material will change. And at the base, the microstructure would be coarser with large number of grains, whereas at the top, the microstructure would be finer. And we are well aware that a fine microstructure has higher hardness, whereas a coarse microstructure with larger grains would usually have lower hardness for the same material. And this is the case here as well. Also, there is anisotropy in some of the other mechanical properties, such as the ultimate strength and tensile strength. And this has been evaluated by taking samples across different orientations and different sections. And it was reported that the Z direction is weaker by about 20% in yield strength and 11% in ultimate strength compared to, say, the XY direction. And this was because of insufficient penetration. And this penetration for the ME1 process actually increases with increasing the current. And a simple logical way to think of this would be that with increasing current, the amount of heat which is getting discharged at the material interface is more, which leads to more melting or deeper melt pools, and thus leads to deeper penetration. Now, some of the defects or the things to look out for in MIG-BOM would be the first would be, say, residual stresses and distortion. And we hear a lot about residual stresses, and there's a lot of research reporting residual stresses, but honestly, very few people actually understand what is happening. So it is actually the stress which remains in the part after the removal of all external forces, so after the build cycle, after any post-processing or finishing operations. And all the external forces are removed. And this residual stress, which remains in the material, may lead to distortion of the part and loss of geometric accuracy, even delamination or complete fracture. Also adversely affects the fatigue life of the part. And yeah, so if this residual stress would be more than the ultimate tensile strength, it will lead to fracture or cracking. If it is more than the yield strength, it will lead to permanent plastic deformation or warping. And why this happens is we know that during the melting of the material, so because of the Gaussian distribution of the energy, the temperature at the center of the bead would be maximum, and the temperature at the periphery would be minimum. And of course, even this minimum temperature is above the melting point and more than the temperature of the solidified part. But once the energy source, which in this case would be the mid torch, it moves away from this region and the bead solidifies, its temperature decreases. And because solid occupies less volume than liquid, the region also contracts. And initially, because of melting and expansion, there was some compressive stress on the surrounding material. And once it solidifies and contracts, there is tensile strength on the surrounding material. And this is also illustrated by the stress strain curve here. So initially, you have these compressive stresses on the surrounding material. They plateau or reach a constant value. But once the energy source is removed, these stresses turn tensile. And what will happen is if some compressive stresses are present in the material or in the part, if there is any crack, the compressive stresses will, of course, try to close it. Say you have a part and there is a crack, pre-existing crack in this, and because the stresses are compressive all around, they will actually try to close this crack. Whereas in the other case, say if you have a part which has some residual tensile stresses and you have a crack in it, the tensile residual stresses will further open it up, leading to material failure or fracture. Of course, it is impossible to get rid of all the residual stresses or relieve them fully. However, there are certain strategies, such as the ones we saw, such as ball peening or laser shot peening, which can help us eliminate some of the residual stresses from the surface. And thus, if these in situ cycles are conducted after deposition of each layer, it can minimize the total residual stresses in the part. Another common defect in MIG worm and actually in all additive manufacturing processes is porosity. And it will lead to low mechanical properties and low fatigue life. Also, these pores may serve as the coalescence point for failure. And mostly two types of porosities are observed. One is the raw material induced, which can be due to surface contamination. The other can be process induced due to some poor path planning or unstable processes. And the following parameters must be kept in mind while addressing or while controlling these porosities. So for aluminum, when we are trying to deposit aluminum, we should use an AC source to help us break the oxides, or we should use the cold metal transfer process. Again, the quality of shielding gas should be high because even the gas can get entrapped, or if it is contaminated with some other substances, they can get trapped and they can get liberated during subsequent material deposition and thermal cycling, which can lead to pores. For instance, hydrogen porosity is very commonly observed. The piping should be non-organic because again, similarly, the organic piping can actually react with the material deposited, or because of the high temperature, it can actually liberate some gases which can get trapped. The wires and substrates should be very clean. So recently, there are many papers coming out which actually try to correlate the quality of the surface quality of the wire with the final quality of the finished part, and there is a good correlation between the two. So, feedstock wire which has good surface finish to begin with actually leads to say low porosity in the final parts. The feedstock quality should be high. The bead shape should be optimal, and this here it is illustrated in terms of the contact angle or the wetting angle. So for a suitable wetting angle which is lower than 90 degrees, the deposition of the next bead at a suitable uh, step over distance would actually ensure that there are no voids or no areas where material is not present. However, if the wetting is low and the angle is such that, say, yeah, it is lower than 90 degrees, in such a case, any deposition of the subsequent bead at a step over distance would actually lead to certain void here, which will not be filled and will continue to remain as a pore. The in situ process monitoring or some of the post-processing techniques may also be used to get relieved from these pores, but they are inevitable and some porosity will always remain in AM-based parts. Again, cracking and delamination are frequently observed. Two types of cracking which are discussed here are the solidification crack and the grain boundary cracking. And delamination between the subsequently deposited layers can happen because of incomplete melting or incomplete penetration of the pre-built layers, and this cannot be repaired. Especially this is commonly observed in the powder bed fusion processes. And one way to overcome it is preheating. Again, not all defects affect all materials equally, and some materials are more susceptible to different sort of defects. So for the case of aluminum, porosity, which is highlighted here in purple. So porosity as well as residual stresses are major concerns. However, delamination is not really a big concern. So this is something called a radar chart. Here the number 1 indicates slight inconvenience, whereas 5 would indicate a major error. For titanium, which is highlighted in red here, we see that oxidation is the primary culprit, whereas it does not suffer much delamination. The residual stresses are intermediate, and even the porosity is pretty low. Similar for other materials. So based on our target system or the material that we are depositing, we should take necessary care to address the associated errors. The subsequent slides actually highlight some of the machines which use different kinematics or multi-axis kinematics. So this is a three-axis CNC with MIG-BOM. So this machine is actually developed at IIT Bombay by Professor KP Karunakaran and used here. Again, we may use some multi-axis kinematics or 5 degree of freedom table to totally eliminate the need for any support structures. Or instead of multi-degree of freedom table, a robotic manipulator or robotic arm may be used. So here at IIT Bombay, we also have a 6 degree of freedom robot, which deposits both wire and powder material in the lab of Professor Ramesh Singh. And there, the setup uses a uh, fixed staple, and it is the robotic manipulator which actually moves around and deposits the material to obtain the necessary geometry. Again, the kinematics may also be different. So here we have a parallel kinematics or a delta robot based MIG-worm machine, and even hybrid kinematics may be used. So by using a combination of the parallel kinematics, such as here in this CZ layer, which is in working in conjunction with this serial kinematics. Now, the next topic covered this week was tungsten inert gas welding or plasma WAM, and most of the defects or most of the process modeling might be similar to to MIG WAM. The setup is of course noticeably different, and here the primary difference is that the electrode itself is non-consumable and is made of tungsten, and a consumable wire is fed separately from the side. So it consists of a welding torch at the center, which is actually the tungsten electrode, and it is of a non-consumable type. And inert gas is supplied to the welding zone through an annular path to effectively displace the atmosphere or oxygen surrounding the molten pool. And filler wire is fed towards the molten pool from a side. and this leads to problems which we'll encounter in the subsequent slides. And typical deposition rate in TIG-based bomb is some 15 to 30 gram per minute. So it is actually the MIG and TIG and plasma bomb based processes which actually have sufficient deposition rates for actual industrial scalability. And it is these processes which may actually lead to say commercialization of AM in the coming decades. Other processes such as say this fat photopolymerization or even for metals, say powder bed fusion, the build times are so high and the deposition rates are so low that they don't really have much industrial scalability. Of course, for small volumes and high customization, they're very well suited. But for volume production, yeah, it is actually the bomb-based processes which have industrial feasibility. And since the electrode is non-consumable, we would actually want it to last for a long time, and we would not want to change this frequently. This can be accomplished if we have most of the heat liberation at the workpiece rather than at the electrode itself. Even though tungsten will have a very high melting point, but even then, because of continuous heating up, it can get oxidized and can lead to shortage of will shorten its life. So mostly a DC electrode negative or AC current is preferred for the case of TIG-based bomb. And when a step pulse DC is used, the current level is maintained at two levels. So this is similar to what we already saw. There's a background current, say corresponding to this low level, and there is also peak current. Now, plasma cladding is similar to TIG cladding and also uses a non-consumable tungsten electrode. And in TIG welding, the inert gas is used only for shielding, whereas in plasma welding, the inert gas is also the source of the energy or the plasma, as the name suggests. So because of the very high, so yeah, in plasma welding, the shielding gas is divided into two parts, into the inner core for ionization and actually establishing the arc. So because of the very high temperature, the inert gas actually turns to plasma. Plasma consists of ions and electrons separated from each other. And this plasma actually goes on to melt the fed wire as well as melt the substrate. And some additional inert gas, which is supplied from the outer core, again is utilized for the shielding purpose or for protecting the melt pool and the molten material from oxidation and contamination. And plasma is indeed more popular because in this case, the tungsten tip is not really projected outwards and the bead height can be increased significantly. So for the case of this plasma-based TIG, say the tungsten electrode would be somewhere inside this. It will not be protruding out of the nozzle, as was the case previously. So here we see that the tungsten is actually protruded to a good extent. Because here the electrode is within the nozzle itself, the working distances and the deposition heights can be changed significantly. So here is a figure of the TIG or plasma-based worm setup. Again, so just like very similar to MIG worm, any modeling or any optimization exercise for a TIG-based worm process would include a few very fundamental experiments. The first would be a single bead experiment to determine the bead height, the bead width, the depth of penetration, and to see the how well it is bonding with the substrate. The next step would be to optimize actually multi-bead deposition to find the optimal step over distance to see if there are any voids forming between the adjacent beads. Once these two are perfected, we can move to a multi-layer experiment where we deposit a few layers on top of each other, see how they are fusing or bonding with each other, if there is any interlayer delamination or porosity present, or what is the final height that I'm achieving after depositing any, say, n layers. Of course, we saw that it will not be equal to the simply not be equal to the uh, n multiples of the height of the first bead because this first bead would be considerably higher. But the subsequent, say this is H1, and the subsequent beads would be say H2, H3, and so on. So generally Hn would actually be less than H1. That's the total height. would it be some h1 times certain times this subsequent deposition heights. So it's not the case that they will always be equal, but because of our simplified model, we found that the heights of each of these subsequent beads were also equal. But yeah, what can we can say for sure that it will be not be simply a multiple of the first bead height. Anyone wants to say something? Karthi, could you please mute yourself? Thank you. And similar to this big worm process, even the parameters which are actually dictating the process or governing it are pretty similar in terms of they would be related to the power, the gas, the deposition strategy and rate, as well as the torch speed. And yeah, as we discussed, the modeling would include optimization of the single bead, multi-bead XY plane, and multi-bead Z plane deposition. Now, another important consideration here is that since the wire is being fed from the side, depending on how quickly or how slowly it is being fed, three scenarios may arise. If the wire is being fed too slowly, or if the temperature in the arc is too high, the wire may melt midway and will simply get deposited a little distance away from the intended region. This is known as droplet transfer. Another extreme case may be that the wire is being fed too quickly and it does not get adequate time or it does not interact with the arc long enough to actually get melted fully and simply goes and collides with the melt pool in a semi-solid state. This is called wire plunging, and this will lead to over deposition as well as discontinuity in the beads. And what we ideally want is something called a bridge transfer, where a continuous bridge of this molten material is being deposited. So neither is the molten droplet totally separated from the incoming wire, as in the case of droplet transfer, or nor is it in this semi-solid type of state, such as in the case of wire plunging and colliding with the melt pool. It is getting transferred at a constant rate. So this bridge transfer is actually the most suitable or most desirable type of transfer. And even these three scenarios can be predicted based on some simple models, as has been done by Gang et al. In this paper. And based on their model, they could identify under what conditions will we have each of the three scenarios when will it correspond to say a droplet transfer case or a wire stubbing case or a bridge transfer case. And this is the flowchart. Again, based on this simple model, we have an example numerical here. Also, the defects or the issues which plague this TIG-based worm are again similar to MIG. So they would include the residual stresses, the porosity, and crack and delamination associated errors. Another error which is unique to TIG-based worm is actually the lack of omnidirectionality. So this omnidirectionality is not the error. Actually, it's the lack of this omnidirectionality which is the problem. And omnidirectionality would imply that the material properties or the deposition process itself is, say, similar or identical, irrespective of the direction along which we are traversing. But this is not the case. So the term omnidirectional would actually indicate an equal sensitivity of the process in all directions. For instance, if we have an omnidirectional antenna, it will receive or send signals equally well in all the directions. However, in tick-based worm, we see that this wire is actually fed from one of the sides. Thus, depending on how we are moving, things may change. So here we have the deposition head moving around in a circular orbit. Say this is my position 1, this is 2, 3, and 4. Thus, I'm moving in a clockwise fashion. And when I am in position 1, I see that the wire is being fed. So here, the direction of the head, deposition head would be tangential to this locus. And here at this instant, when it is at position 1, the head is moving along this direction. Thus, we see that in this case, the wire is actually being fed from the back of the torch. And this corresponds to the case of back feeding. In position 2, again, so the tangential direction is along here. And we see that because the direction of feeding of the wire is fixed, it's just the head is moving around in this plane. So for the same fixed side feeding direction, the feeding direction, now for position 2, this amounts to a case of side feeding. For position 3, because of my clockwise motion, the tangential direction would be along this as indicated, and the feeding direction of the wire again remains fixed. Thus, in this case, we see that the wire is being fed from the front. And finally, in position 4, we see that again the wire is being fed from the side, and thus we see that there is a potential for anisotropy in all the four directions and along the trajectory itself. And it has been very well quantified. So here we see that on the figure to our left, here is the reference slot in yellow between which the material should have been deposited. The path of the torch is of course concentric with this reference slot. However, we see that the bead is not really equally distributed about it. So at certain regions, say here, we see that the bead is distributed equally about the center line. But in other cases, we see that there is a large lack of omnidirectionality. Here, the bead is totally on only one side of the track. And this has also been quantified in this figure to the right. So the deviation in width and the deviation in height have both been quantified, and we see that the errors are pretty large. So it's not negligible and definitely will affect the final bead, the final deposition characteristics as well as the final material properties. Now, this lack of omnidirectionality can be overcome by a few strategies, some more feasible or more popular than the others. So one of them is this coaxial feedstock with fusion source. So here the feedstock is simply being fed through the middle uh, of the tungsten electrode. So we can maybe use a hollow electrode and through which the wire can be fed. Second can be a coaxial fusion source which is surrounded by a feedstock, or its converse, the coaxial feedstock which is surrounded by a fusion source. Again, a similar idea, but a more annular in this case. And the next is actually a dynamically adjusting feedstock feeding direction, which is the most popular and the most well implemented case. So here we saw that in this case, the wire feeding direction was fixed and it did not really adapt to the direction of motion of the deposition head. And that is what was leading to the errors. But if we see that once the direction of the deposition head is changing as we move along this path, the deposition head will always be tangential to the path. And with the change in this motion, if I can also rotate my feedstock by the same angle. So say if the head is displaced by a certain angle phi, if I can also displace my feedstock rotation angle by an angular displacement of phi, then I will ensure that such omnidirectionality is obtained and the anisotropy is eliminated. So here you have a few design and schematics of the some of the cases previously discussed. So here we have multiple feedstock wires which are being deposited or which are being fed into that fusion source. And depending on which direction I am moving, or irrespective of the direction, if I supply the feedstock through these three nozzles simultaneously, I will achieve omnidirectionality. Or we can move the turntable or rotate the turntable to ensure that omnidirectionality is obtained. Or we can simply move the direction of the wire feeding itself, as we discussed. So if you attach a bearing and constantly rotate or adjust the angular position of the wire feeding, omnidirectionality can be obtained. Again, it may also have similar subsystems as MIG welding, such as 3-axis or 5-axis systems or serial or parallel kinematics. Here are some of the case studies of practical applications of TIG-based one. In the final lecture this week, we looked at electron beam based additive manufacturing. And this is pretty interesting because for the first time we are coming to actually using particles for this purpose. And we are well aware that electrons are actually very light particles. So how are they able to transfer the sufficient amount of energy to the substrate or to the deposited material to actually be able to melt them? And it is through the kinetic energy, which they transfer to the substrate or to the deposition material. And the velocity of an electron can easily be increased to about two-thirds the speed of light. In fact, if we keep increasing, so I think this is 10 power 6 for a sufficiently high acceleration voltage, we can even begin to approach the speed of light. Of course, we'll never achieve it, but we can begin to approach the speed of light. So it is because of the very high speeds of these particles that they transfer sufficient energy to our system for material deposition. And before they transfer any energy to our system, they have to be generated first. And electrons can be generated or emitted from substances by various ways. So some of them are illustrated here. The first is the very common thermoionic source. So say something similar to what is used in a tungsten scanning electron microscope, where you have a tungsten gun and you heat it to a very high temperature. Because of the high temperature or the high heat input, the electrons are generated or they collect at the surface and are further extracted. There can be photon-based source where rather than heat, we are getting some photon energy or say like a laser energy, which leads to again the overcoming of the work function and the emission of the electrons. We can also bombard our target material with some secondary electrons, with some primary electrons, which can actually lead to the emission of secondary electrons. And another popular method, which is used in conjunction with thermionic source, is the plasma-based source. So the plasma would already contain some ion, say M plus species, and some electrons. And rather than generate, what we'll have to do is simply extract or segregate these electrons from the plasma source, and those can be utilized for our further need. And for thermoionic emission, Richardson's law actually dictates what will be the current density emitted from the emitter surface, and it depends on the absolute temperature of the emitter, true, the work function of the emitter material, and other factors. So as we were discussing, mostly the thermionic gun or the plasma-based gun are commonly used and encountered in electron beam-based bomb systems. And some other technologies such as Arcum and Siaki use thermionic guns, whereas X-beam is one using a plasma gun. And if we compare between the two sources, so a plasma gun has higher current density and it is two orders or one order higher than the one for thermionic gun. And this is because here the electrons are already present and we are simply extracting them through a very small orifice because of the large density of electrons as well as this very small area through which we are extracting them. The current density naturally becomes high. Again, the acceleration voltage needed for imparting sufficient energy to electrons emitted from a thermionic source can be as high as 150 kV, whereas for a plasma gun, it needs considerably low acceleration voltages. For thermionic gun again, we need a very high vacuum, and the necessity of this high vacuum is because of two reasons. First, as we saw, the electrons are very light particles, and if there are any other molecules present in the chamber along with electron, they will get easily scattered and they will lose their kinetic energy very quickly and will not really reach the target surface. A second reason is that because of the very high temperatures which we subject the cathode to in the case of thermionic guns, it is susceptible to oxidation. as well as reaction with any other species which might be present. To eliminate such chances, we need a very high vacuum in the chamber to prolong the life of the cathode source. Again, even then, the life of a thermionic gun is shorter as compared to plasma gun, almost half, and the cost is high because of the high vacuum aspect. So to have a high vacuum system to maintain it and to run it all the time, the costs would be high. However, they have similar applications. And this was only about the generation of the electrons or emission of electrons from the cathode source, but they also need to be focused and accelerated towards the surface. So electrostatic fields are used for the extraction and acceleration, and magnetic fields are used for focusing, deflection, and correction. Even then, these deflections are not very large, and the deflections are small. Mostly, the traversal of the beam on the surface is achieved by movement of the build plate itself. And of course, the Lorentz forces are the governing forces in this case. And from cathode to the anode, the extraction focusing is done by electrostatic forces. And then from the anode to required area or the required surface by electromagnetic forces. In the first stage, where they are just extracted from the cathode and are accelerated, the magnitude of the electron's velocity increases due to the electric field. And second stage, where they are deflected as well as accelerated, the direction of the velocity is changed by the magnetic field. So yeah, they're not accelerated in this case, only the direction of the velocity changes. The magnitude remains the same. So acceleration only occurs till the anode, and after that, this acceleration would actually lead to change in the magnitude of velocity. And here the acceleration actually corresponds to the change in direction. Now, as we were discussing, why there is a need for vacuum in either the thermionic source or the plasma-based source. So electrons should be focused to achieve the required power density. If other molecules or other species are present in the working chamber or in the gun chamber along with the electrons, they can be very easily scattered because of their light weight or light mass, and they will not reach the target surface. And secondly, because of the high temperatures encountered, the filament is readily susceptible to oxidation or thermal damage. Thus, the presence of any foreign molecules should be necessarily avoided. To achieve vacuum, different sorts of pumps can be used. So, if any of you have worked with any vacuum system, you would be familiar with some of the names. So, for achieving low vacuum up to 10 to the minus 2 millibar, we have rotary pumps. Operating in a similar range is Roots pump, and for achieving the higher vacuum, we have diffusion pumps or turbomolecular pumps. The working principle of some of the pumps is also illustrated here. So the rotary pump obtains by a rotary mechanism, and here this is our target area. So this is the working chamber from where we are trying to eliminate the heat. It's at a low pressure. From where we're trying to eliminate the air, and it gets pulled into the pump, gets transported towards the other chamber where it is compressed, and once a certain critical pressure is achieved, the air is eliminated from the other valve. Thus, we are constantly sucking out air of the low pressure working region and eliminating it or discarding it, say, to the atmosphere. Similarly, the roots pump also works on a similar mechanism. However, instead of this rotary system, it uses the rotary motion of lobes, which again sucks in air from an inlet at a low pressure and discards the air to a higher pressure. For generating the high vacuum, the two types of pumps are the diffusion pump and turbomolecular pump. So diffusion pump actually has some oil in it and a heating element. The oil is heated and vaporized, and the working principle is that these vaporized molecule or the gas molecules of this oil will actually adhere to the surface of air, and air is usually light. Because of the adherence of these oil particles or oil molecules, the air will get heavier, and then they can be easily say pulled out by the diffusion pump. Similarly, the turbomolecular pump actually consists of two blades, which are the stator and the moving blades. The stator blades simply give direction to the incoming air molecules, and the moving blades actually say move them out or discard them from the pump chamber and into the backing pump. So neither of these high vacuum pumps are operated alone. They are operated, say, in series with a rotary or a root pump, as seen here. This is the case for both turbomolecular and diffusion-based pumps. Here again, we have certain other schematics of the electron beam-based WAM systems. This is for the CIK type of machine. We see that here it uses a dual wire system and as well as a high degree of freedom table to eliminate the need for any support mechanisms. Now, similar to the case we observed for TIG-based one, the metal transfer may happen in various ways. So one of them would be droplet transfer. The other extreme would be, say, wire stubbing, and the ideal case is bridge transfer. And based on some simple modeling, the critical condition for metal transfer has again been observed. So when the height or the nominal height of the filament above the base metal or the pre-deposited layer is greater than or equal to twice r, where r in this case is actually the critical radius for the droplet. When it is exactly equal, we will have say a bridge transfer, and anyway this should be greater than the critical value. When it is greater, we'll have droplet transfer. If it is less, we will have wire stubbing. And this critical radius of the droplet can be calculated based on the other variables present. And the if we look at the forces which are actually acting on the droplet and from where this equation has been derived. So first, of course, it would be the EB pressure force or the E beam pressure force acting. A second force acting along the negative z direction is the force due to gravity. Again, so there would be some vapor pressure or vapor recoil, which may be because of the gases which are incoming, or because of the emerging of gases from the molten pool itself, which will again act in the positive z direction. And there will be the surface tension, which will actually prevent the molten drop from falling down. And it's actually the balance of all these forces that dictates what will be the critical radius of the droplet before it begins to drop and transfer metal. In EB-based bomb, the scanning speeds are very high. However, some preheating is often needed. This preheating is achieved by scanning the surface by at a diffused spot size. So with a larger spot size and a small scanning time, we can have some preheating of the layer before we actually do the printing pass. And yeah, the printing or the scanning speeds are very high. Thus, deposition rates can be high as well. We also saw that in Siaki machines, they were using a dual wire setup, so that can also lead to an increase in the deposition rate. However, some of the challenges include the residual stress and distortion. As we discussed, this cannot really be eliminated and may be encountered in all of the AM processes. The surface finish is not very good. So because of the stair-step stepping effect, as well as because of the high scanning speeds and high deposition rates, the surface finish can be poor and would need a post-processing step to actually correct to the accurate geometry. There is a need for support material for overhanging parts, and this can be overcome by using, say, a higher degree of freedom multi-axis table. Because of the high temperatures, some of the alloying element materials can also be evaporated, and thus the chemistry or composition of the final deposited part will not actually be equal to my say feedstock material. And just like the other processes, omnidirectionality is again a problem and is not easily achieved. This can be overcome by, as we discussed, the dynamic adjustment of substrate or rotation of the substrate. And similar to tick-based bomb, some centrally fed feedstock surrounded by multiple equally spaced oscillating EBs, or even a hollow cathode beam with a coaxial wire feed can be used to achieve the coaxiality or the omnidirectionality. Here, some of the systems are showcased from a review article in which Professor Kapil is also an author. So NASA was the first organization which developed this wire-based process called solid freeform fabrication, and also the CRG system, the ProBeam system, and X-beam, which is actually the one to use a plasma gun, is highlighted here. So we have come to the end of the content for this week's lectures. Let us take a short break, and after that, we'll discuss a few questions. So let us resume around 8:30. Let us resume. So we have some conceptual questions here. So the first question is asking, in which of the following cases would an AC source of electric power be useful in the context of MIG-based form? So we saw three cases, say between the substrate and the deposition nozzle. The first choice is whether we wish to use an AC or a DC source. And if we have a DC source, the choice is which body to have as negative and which one would have positive. And we know that there is about 70% heat liberation at the anode. So if you want a deep bead or a higher depth of penetration, you would have the substrate as positive. If you want lower penetration and the heat to be liberated around the anode or the electrode itself, you would put the substrate to a negative. In this case, the deposition would be smaller. And if we want some intermediate deposition, we can use actually an AC source, in which case the polarity would be reversed every half cycle. But is that the only use? So maybe AC will have some intermediate depth of penetration, but is that the only use? So for obtaining an intermediate depth of penetration, yes, this will of course be achieved. And for deposition of metals which are easily oxidized. So we know that there are metals such as titanium and aluminum, which despite our best efforts and despite using the inert gas for shielding and other ways, they are so susceptible that they will still get oxidized. And these surface oxides are actually harder and chemically more inert than the base material or the core, and they may prevent further bonding or further deposition process. Thus, it is very important to break those oxides, and because of the continuous reversal of polarity in the AC source, these oxides can get broken up. So even that is a important point for reducing the overall power consumption. So the relationship between power consumption and AC or DC voltage is not really so straightforward. And irrespective of which type of source we are using, the power consumption may be same or even it may be higher for the case of AC. So what we can safely say is that both A and B are the correct statements. The second question is talking about the background current and peak current in pulsed metal transfer. So for the case of both TIG and MIG based one, we saw that it's not necessary to give a monotonic current or even a constant current with time. It can have some step or it can be a pulse. And in this pulse, there will be some minimum current, which actually corresponds to the background, and there will be some peak current, which corresponds, yeah, to the peak or to the maximum current, which is encountered. And each of them have distinct roles. So usually, we saw that how in the case of pulse metal transfer, the metal is actually getting deposited in the form of some discrete drops, and the deposition is not really continuous. So we have a small droplet forming, and with time, it evolves into a larger droplet, and then finally it grows large and is deposited on the bead. So the background current is actually the one which actually maintains, initiates and sustains the arc. So the intensity of this arc it'll first be dimmer and then it'll continuously increase in brightness and then go out or grow very dim and then increase in brightness again. And at every time the brightness is maximum is when actually this droplet is getting detached and deposited. So it is the background current maintains the arc, does not allow it to be extinguished. Whereas the peak current at which we have maximum intensity is when, because of the very high temperature, this molten metal droplet gets detached or segregated, separated from the electrode or from the filler wire and gets deposited. So for the background current, The actually the function is to maintain the arc, and for the peak current, it is to generate the droplet of the molten metal. Since we're talking about both processes, option C is the correct one. Question 3 is also related to the types of the metal transfer in the case of MIG or TIG based one, and is asking that what changes are observed in the case of rotating metal spray transfer as compared to the conventional or simple spray metal transfer. So we saw that in the case of spray metal transfer, the deposition occurs in the case of such almost continuously falling beads, whereas in the case of rotating spray metal transfer, there is some rotary motion associated with the beads, and they may get deposited around in the XY plane. They need not get deposited in one spot only. So one can clearly say that in this case, the bead area would be larger, and because the material is not concentrated at the same region or in the same small spot, the depth of penetration would be lower because I'm not giving the same amount of heat input. Say if I keep the deposition rate constant, so the amount of material input is the same. But in one case, all the material is getting deposited and concentrated in only one area, and it is transferring all that heat energy to the same spot, leading to higher temperatures, and there's a greater depth of penetration. In the second case, even if my deposited volume is the same, it is actually being, say, concentrated over a larger area, and the heat transfer is occurring over a larger area. Thus, the the temperature reached at each point in the area would be smaller, and thus the penetration would be lower. So, for the case of rotating metal space transfer, the depth of penetration decreases, and the width or area of the bit would increase. So, options 1 and 4 are correct. We see that here option C corresponds to the correct option. Here we have certain statements. So these are like assertion and reasoning type questions. And which of the following statements are true regarding residual stresses in warm build parts? So residual stresses are inevitable and cannot be avoided. This is true. So we may have some stress relieving operations through which we can minimize or eliminate relieve some of these stresses, but they can never be totally eliminated, and they are inherent to a part, which is built through this process. Tensile residual stresses are preferable as they inhibit crack growth. So again, I'll just draw a very quick schematic to discuss what we are talking about. If we have tensile cracks, tensile residual stresses, it will try to open up any crack which may be generated or which may be inherently present in the material. So option 2 is incorrect. The compressive residual stresses, on the other hand, if present inside the material, well, mostly the tensile ones are present. The compressive stresses would actually try to close any such crack, and thus it is desirable. So this option is correct. And the compressive residual stresses are more dangerous than tensile residual stresses. So we already observed that so no microsystem is perfect, and each will have some defects or cracks. And if any tensile stresses are present, they will try to open up these cracks, and the cracks will propagate further. Thus, even if compressive stresses are present, they are not really as dangerous as the tensile ones. So again, option 1 and option 3 are correct. So here, option C is the right answer. So question 5 discusses the use of a robotic manipulator against a multi-axis table. And we saw that both of these are actually used to eliminate the need for any support structures. Either we can tilt the substrate or the built material itself so that it is normal or it is tangential to the deposition head, or the other way is to keep the substrate or the pre-built material fixed and actually manipulate our deposition head through the use of a robotic manipulator. But both of these are not exactly identical, and there will be some changes. So what is the disadvantage? Does a robotic manipulator have less degrees of freedom? No, this is not the case. So 6 degrees of freedom robotic manipulators are easily available. It's not the case that they will have any less degrees of freedom. Process parameters may be different for non-overhanging and overhanging parts. So when we are actually using a robotic manipulator, initially say we are depositing vertically, then we change the angle, or it might even happen that we are depositing at such an angle, or even totally inverted in a totally inverted configuration. So what is happening is these cases, say this is corresponding to some overhead welding sort of case. If I have a material which is like this, so I'm printing it layer by layer, and now I've reached this stage where I have to print these flanges. So one way to print it is to go actually underneath and print this. So this would actually correspond to an overhead welding case. And what is commonly observed is that the process parameters for overhanging and non-overhanging parts are not same. So we will have to continuously monitor, continuously change or optimize the process parameters, which will be a hassle. Difficulty in maintaining inert environment. So the entire working area or the working envelope can be shrouded in inert gas, and this is not really a problem. Smaller build volume, so we can have very large robots. In fact, with robots, I think the work envelope or build volume can even be larger than just by using a multi-axis or multi-degree of freedom table. Because even this is not correct. So the only change is that we will have to have separate optimized parameters for overhanging and non-overhanging regions for the case of the robotic manipulator. For the case of just simply tilting the table by using a multi-degree of freedom table, the process parameters are the same. In fact, it is most commonly used, and in my own lab, we have a 5 degree of freedom table, and the deposition head parameters remain constant. Question 6 is asking why are the hardness values of the first few layers of a component deposited by MEGWAM nearly constant? So this deals with the phenomenon of thermal cycling. We already saw a couple of slides on thermal cycling and saw what is happening. So because of the deposition of the subsequent layers, even the previous layers are seeing or are subjected to a rise in temperature. Often, this temperature may not be equal to the melting point, but only say a fraction, say 20% of the melting point. But even that can lead to some sort of in situ heat transfer and change the microstructure, as well as it may affect the elemental segregation or the microsegregation and can change the material properties. Of course, during the deposition of the immediate next layer, temperatures very close to or equal to the melting temperature are achieved, and that leads to complete melting. This remelting and resolidification again may lead to a redistribution of the alloying elements. But what is its effect on the hardness values? So the first few layers undergo thermal cycling, leading to coarse microstructure and low hardness. This is true. We know that the coarser the microstructure or larger the grain size, the hardness value will be low. And rather, if you have a microstructure of the same material with smaller grains, or even like acicular type or needle type grains, the hardness would be far higher. The first few layers undergo thermal cycling, leading to fine microstructure and low hardness. No, this is not the case. So fine microstructure is corresponding to higher hardness. And similarly for the others, so coarse microstructure and high hardness, this is false. Fine microstructure and high hardness, this is achieved for the top few layers, not the first few. So even this is incorrect. So it's because of the thermal cycling, which generates a very coarse microstructure with large grains. And these grains have a lower hardness, even if the material composition remains the same. Question 7 is asking, why should we use non-organic piping in the context of MIGWAM? So if we remember, this corresponds to actually the porosity type error, which is observed in the MIGWAM parts. And even though some degree of porosity will always be inherent, we cannot have 100% dense parts. Even for builds claiming 99.9% dense, if you look at simply the optical density or the area density, you'll often find that some form of micro density is always present or micropores are present. So they can never be totally eliminated, but yeah, they can be reduced. And non-organic piping in the context of MIG-BAM, will they have lower cost? Not necessarily true. Will they be less reactive with common build materials deposited by BAM? So these common built materials may be equally inert or equally reactive in the case of say titanium and aluminum with either organic or inorganic piping. Even this is not a generally true statement. They prevent process-induced porosity in the deposited part. Yes, because of the high temperatures encountered in these processes, the organic type of piping may lead to evolution of certain gases. What happens is in the molten state, these gases are soluble in the metal, so they get soluble. They mix into the molten metal. But when the metal solidifies, these are not as soluble in the solid state, so they get liberated. Now, since the metal has already solidified, often these gases may remain as remnants inside the solidified microstructure and may lead to some gas bubbles. Or if there is a way for these gases to escape, then they escape and leave behind porosities. So, any trapped gas, even if it is the inert gas or any liberated gas which comes from or evolves from the organic piping, may lead to porosity. And non-organic piping produces gases which assist in the warm process. So this is incorrect. The only gases which we need in the warm process are the inert ones, which may be used either for the generation of plasma or for the shielding of the melt pool. Thus, option C is the correct one. Which of the following statements are true in the context of vacuum generation in e-beam based warm systems? So we saw that vacuums are important because of two reasons. First, the electrons are very light particles, and if they come in contact with any heavier molecules, they will simply get scattered away. They will not really reach the target surface, and the printing will not happen. The second case is that in certain cases, such as for the thermoionic source, where we're actually subjecting our filament to very high or extremely high temperatures, maintaining vacuum is necessary because at such high temperatures, the reactivity or the susceptibility of the filament will be very high. And if any other molecules are present, the filament can get easily oxidized, leading to very short life for the filament or even some combustible reaction. Thus, it is very important to maintain a high vacuum. So we have certain statements here. The diffusion pump can contaminate the gun chamber. So while discussing the operating mechanism and working principle of the diffusion pump, we saw that it contains some diffusion pump oil, which is heated by some source, air resistance heating source. Upon being heated, the oil molecules get vaporized, and inherently the air molecules are lighter. When these vaporized oil molecules adhere to these air molecules, they become somewhat heavier, and now the pump can more easily expel or eliminate these air molecules. However, if somehow these vaporized oil vapors or oil molecules they enter the gun chamber, again it will lead to contamination. The even oils are say organic compounds, fatty acids or fats, and they can actually say react with the filament material apart from scattering away the electrons. So they can definitely contaminate the gun chamber. This is the correct statement. Turbomolecular pumps are mostly used in the working chamber. So we saw how even though both working chamber and gun chamber need vacuum, the necessity for vacuum in the gun chamber is higher, so we need a higher degree of vacuum. In the working chamber, we are content with vacuum of say 10 to the power minus 5 millibar. So, same as the typical FEACM systems. Whereas for the gun chamber, you need vacuums of 10 to the power minus 9 millibar or so. So this is not correct. Diffusion pumps alone are mostly used in the working chamber. While diffusion pumps are used in the working chamber, they are never used alone. They are always in series with a rotary pump or a roots pump. So because of this phrase alone, even this statement is incorrect. And turbomolecular pumps can only work in some specific orientations. This is true, and it was also mentioned by Professor Kapil in his lecture. We saw that in turbomolecular pumps there are some stator blades and there are some rotor blades. And under some specific orientations, the stator blades actually lead or direct the incoming air molecules into the rotor blades, which then further sweep them away out of the region of interest and expel them into the atmosphere. So statements 1 and 4 are correct. So option C is the right answer. Question 9 is asking us, why does the electron beam based worm system developed by CRK Inclusive use dual wires? So in the schematic, we saw that dual wires were present. But what can be the possible reason for using these two wires simultaneously? Because mostly we find that only one wire is incoming. So can it be used to increase the material deposition rate? True. So maybe I can deposit, if I deposit the two wires at the same feeding rate, I will simply double my deposition rate. Or if I modulate the speeds, I can have certain multiple of the deposition rate if I was using only one wire. So in the case where I need very quick build times and very high deposition rates, I can use the two wires simultaneously. To achieve omnidirectionality, so while this will not really be as effective as using three wires displaced at angles of 120 degree to each other, it can still help in some to achieve some degree of omnidirectionality, because as we saw that there are cases of back feeding, side feeding, front feeding, and feeding from the other side. At least some of those cases can be taken care of by using or by strategically placing the two wires based on the geometry that we are trying to print. So even this may be true to make FGMs. So if we use the two materials or the two wires of different materials, we can have some FGM or functionally graded materials printed. By changing the deposition rate or by modulating the deposition rate, we can even change the alloy composition, or we can even generate some new alloy by some in situ chemical reactions, which may be suitable for additive manufacturing. And all of these are some active areas of research. Thus, it may be said that all of the above statements are the probable reasons why the WAM system developed by CRK Inclusive uses dual wires. So that is all I had for today. I would be happy to take any questions, should you have them, related to this week's content.
Sir, I doubt in lecture 1, in first
Okay,
lecture,
Indrajit.
metal.
Yes, I'll just share the slide.
Actually, sir, in page number 23,
Yes,
here, sir, Professor Kapil have written that energy required for melting wire plus energy required for melting substrate is the
yes.
total energy. But the calculation is part, I think, is wrong. Could you please check the calculation part for energy required for melting wire?
Oh, so you are saying that there might be some problem in the numerical values and the final answer which is coming.
Yes, sir. Yes, sir. And also, I have seen that in assignment, which all the options are given, that is wrongly put, sir. In assignment, because in
Okay.
assignment this type of problem is given. So
Yes.
in the assignment, that is I have seen that option is wrong.
Okay, so I have observed that even for some of the previous assignments, I think the options were revised and the marks were accordingly assigned. So I think it would be a good idea to raise this in the discussion forum, and they will take suitable action. Meanwhile, I'll also check this calculation and I'll get back to you. And if it is indeed wrong, maybe we can correct it.
Okay, sir.
Yes. So yeah, please raise that in the discussion forum. So they will revise those options or like eliminate the question or give marks accordingly. Yeah.
Yes, sir. Yes, sir. But sir, at this moment, you can could you please check the? Achha, okay, 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 sir.
No, I mean I will definitely check it. So I do not really have a calculator at hand, but I'll definitely check it and come back to
Okay,
you.
okay, okay, sir. Okay, sir. Thank you. Okay, sir.
Yes, yes. If there are no further doubts, we'll stop here. Thanks for tuning in, and I hope to see you again next week. This
Okay, sir.
is the
Thank you,
live
sir.
session for, yeah, thanks, Indranil. This is the live session for Fundamentals of Additive Manufacturing Technologies, and I'm Sourav Goswami from IIT Bombay. Thank you.